Good morning everyone. Okay, the one thing that kinetic energy and potential energy are there. First I will revise the yesterday class here. Here the potential energy of the simple pendulum, its form is directly 1 divided by 2. M is the mass of the body or mass of a particle, and omega square is the angular frequency and its displacement of the particle, that is y square. If you write here the m into omega square is equals to k, then become what? This is 1 divided by 2, k into y square is there, where k is nothing but the constant. Okay. Another one is the potential. Another one is kinetic energy. That kinetic energy is in the form of 1 by 2 m into omega square into a square. It is a maximum kinetic energy, minus of 1 by 2 m into omega square into y square is there, because the kinetic energy is depends on the velocity of a particle here. The velocity equation is v is equals to omega into root of a square minus of y square is there. Then 1 by 2 m into v square. V square is nothing but omega square into bracket a square minus of y square. If you substitute this value of v in that m, k is equals to 1 by 2 mv square. This become like this. Then if you write again the m omega square as a k, then our form is 1 divided by 2 k into a square minus of 1 by 2 k into y square, or 1 by 2 k into k is common here. Its equation is again what? A square minus of y square. Same. Then using these two, or these two are equation number 1 and these are the equation number 2. Call this one equation number 1 and equation number 2. If you want the total energy of the simple harmonic motion, the total energy of simple harmonic motion is the sum of kinetic energy and the potential energy here. The total mechanical energy, is equals to what? Sum of kinetic energy and the potential energy is there. If you write the total energy, right here TE, kinetic energy is here. You can take in terms of k or in terms of m omega square. You can take any one. First I take here the k into omega square. K into a square is there. 1 divided by 2 k into a square minus of 1 divided by 2 k into y square is there. This is the kinetic energy, and potential energy is also there. 1 by 2 k into y square. Here minus 1 by 2 k y square and plus 1 by 2 k y square gets cancelled. Then remaining, the total energy become what? Here the total energy is equals to 1 divided by 2 k into a square is the total energy. Or you can write this one, or the total energy is equal to k is equal to what? M into omega square. 1 by 2 m into omega square into what? It is a square is there. This is the total energy of the simple harmonic motion. It means what? Sum of kinetic energy and the potential energy is there. The total energy of the simple harmonic motion. We have to draw one diagram for this one. One graph of the total energy. It is a combination of what? The kinetic energy and the potential energy. Here it is a maximum point of potential or kinetic energy here. This is the time axis. Okay, our graph is for total energy, but it is the sum of kinetic energy and the potential energy here. It is called the mean position of a particle. When it starts from here, at mean position, we already know that at mean position means at y is equal to 0. At y is equal to 0, the potential energy is equal to what? At y is equal to 0, potential energy is equal to what? Again is 0. Then what about the kinetic energy? The kinetic energy at y is equal to 0, it means at mean position, kinetic energy is 0. It means, if y equal to 0, kinetic energy is. The kinetic energy, y is equal to 0 here. If y equal to 0, m omega square into a square is there. Or 1 by 2 k into a square only, because y is 0. Then kinetic energy is equal to what? 1 divided by 2 m into omega square into a square, or which is equals to 1 by 2 k into a square. This is the maximum kinetic energy at mean position. At here the potential energy is 0, and at here the kinetic energy is maximum. Now here the kinetic energy equal to 1 divided by 2 k into k is here. Small k is a constant, capital K is the kinetic energy. K into a square is there. Okay. Here the potential energy what? 0. If you take the remaining part, the other one is, if we take the y equal to a, at extreme position the displacement is maximum. If the displacement is maximum, then substitute the value of y as a here. Here y is equal to a, so substitute here. If you substitute the y is equal to a, this equation potential energy equal to 1 by 2 k into a square. Again what? At extreme position what? The potential energy is maximum. Potential energy what? Maximum here. Then at extreme position, consider y is equal to a. Substitute in the equation of kinetic energy. If you substitute the y is equal to a square, 1 by 2 m into omega square into a square, and 1 by 2 m into omega square into a square is there. These two gets cancelled, then kinetic energy is equal to what? 0. Here the potential is equal to 1 by 2 k into a square, but the kinetic energy is 0 at extreme position. It means the kinetic energy of the particle is 0 at extreme position. Here at extreme position means that t is equal to what? T by 4. At this position what is the angle here? Pi by 2 is there. Pi by 2. The remaining part, if you calculating that same, y is equal to 0 and y is equal to minus a, then y is equal to 0 again. Mean position, extreme position, mean position, extreme position. If it is plus extreme position, it is positive extreme position. After it will become what? 0, that is the mean position. Then after that, negative extreme position. After that, mean position. After that, positive extreme position. Like that. If you write here like this, at mean position is there, that kinetic energy is maximum. At extreme position, kinetic energy is 0, and potential energy is maximum. After that, here then mean position. If you write the mean position, next is this is like this. The graph will like this. Again, the kinetic energy is maximum at mean position like this. Again here, the potential energy is maximum at extreme position. The kinetic energy is 0 at mean position. Like this, the graph will obtain for the total energy of a particle, which is equal to what? The maximum value. That maximum value, total energy, is equal to always what? M into omega square into a square, or it is equal to 1 divided by 2 k into a square is there. The kinetic total energy is always what? Maximum here. If the total energy is always maximum, then what about the frequency of that? Here, the frequency of potential energy and kinetic energy is always twice the what? The potential energy, or twice the frequency, twice the initial frequency of that. if the frequency of an initial energy is it is considered as a nu. Okay, if you sum up, it is the kinetic energy and potential energy are there. The frequency of the kinetic energy or the potential energy is always twice the initial frequency of the particle. But for the for the total energy of the particle, the frequency is always 0, because here the amplitude is what? Maximum. If the displacement is what? Maximum. Okay. In this, I will write here one important note. The frequency of kinetic energy and the potential energy is always twice the initial frequency. But second condition is there. Second condition, the frequency of total energy is always 0. Always 0. For total energy, that nu is always what? 0 here. Okay. Now, it means what? If the frequency is 0, what about a time period? The time period is nothing but what? It is an infinite, because the frequency and time period both are what? Reciprocal to each other. I'll remove this one. This is the total energy, and the total energy of the simple harmonic motion, and there is a graph which is continuously maximum. The total energy is always maximum. The next thing is very important one, that is the spring pendulum. The spring pendulum is nothing but when a certain mass is there, a small amount of mass which is suspended freely, or which is suspended freely with the help of a massless spring. Consider the mass of a spring is 0 here. We have to consider the mass of a spring is 0. One thing, another thing is the spring pendulum. We have to take here the spring pendulum. Here it is a spring pendulum. It is nothing but, very simple definition is there. When it is a rigid support, when a mass, a certain mass, a small mass is there, the small mass m is there, which is suspended with the help of the massless spring. Consider this mass of the spring is 0, and it has a constant. That constant is K, that is called spring constant. And here this mass is suspended with the help of a massless spring. This is called what? Spring pendulum. What is the definition of that? A small mass is suspended with the help of a massless spring. Massless spring is called a spring pendulum. A small mass is suspended with the help of massless spring is called what? Spring pendulum. Is called spring pendulum. But if it is a spring pendulum, there is a spring constant K, there is a small mass M is also there. If you apply or if it is suspended freely, the one force is applied on this body, that is nothing but the weight of this body. The weight of the body is always directed towards the ground, that is nothing but M into G is there. mg is a force here. And draw another diagram. That is the same diagram is there. One thing, the spring is there whose spring constant is K, which is attached to one, the small mass that is M, that is always directed towards the ground due to the gravity. It is always directed towards the ground due to the gravity. That is called what? The weight of the body, that is mg. But if it is mg, opposite to that, there is called tension. Okay, that is called tension. Alright, also consider this is nothing but the restoring force. Consider this is a restoring force. Why it is a restoring force? If the spring is just suspended like this, or the mass is just suspended like this, if its weight considers this weight as a 5 kg. When it is suspended, it is considered, it means what? Its length is considered the length of the spring as a L here. L is a spring, length of the spring from here to here. Okay, you can take here from here to here. It is length of the spring. When it is suspended, due to this its weight, that length of the spring is just increased like this. It means what? It is elongated. When it is just elongated like this, its length is what? It just increased. It means what? The second diagram is when the spring is elongated, its length starts to just increase like this. It means what? That body is displaced certain distance. It is considered, this is the initial position of that body. Its displacement considered as a y. Okay. This is what? The displacement of the body, displacement of the particle here. But the length of the particle is become what? It just changed like this. Length of the spring is just changed. It is due to what? It is due to the weight of the body. But after certain time, after a small intervals of time, what happened? The spring gets compressed like this. Compressed means it goes up. It goes up. It means it is continuously what? Oscillating. Consider this is a continuously oscillating like this. Elongation, compression, elongation, compression, elongation, compression is there. Okay, that is called oscillation of a body. When it is just compressed like this, when it is compressed, the spring length is just decreased, but the displacement of the body is same when it is elongated. It means what? This is the y displacement of the body from initial position. The displacement when it is elongated is equal to the displacement when it is compressed. Both are same here. These two displacements are always same. Always same. One thing is very important. That thing is, if you consider if the massless spring is there, or the mass of the spring is considered as 0 here. If the massless spring is there, the massless spring is there, what happened? It is considered massless spring is there, then the restoring force is the same at everywhere. It means what? Everywhere. It means here, at every point of the spring constant is always here. The mass is massless. The spring constant is always what? It's constant. Another one is the spring. It is called what? The force is there. That is the restoring force is there, or it is also known as the restoring elastic force, because it always obey Hooke's law. When you rubber is just elongated like this, when deforming force is just removed, it gets its original shape and size. Here also same. When the applied force is just removed, it gets its initial position. After that it gets compressed. Okay, initial position. Or it is nothing but what? It obey always the Hooke's law. The restoring force is same everywhere. And this spring pendulum always obey Hooke's law. The spring pendulum always obey Hooke's law. Hooke's law is nothing but what? Hooke's law, here the stress is directly proportional to strain within an elastic limit is there. Okay, then it means what? The elongation, the displacement of the particle. There also you take in a spring or in that work power energy. We discussed about the potential energy of a spring. That potential energy of spring, the restoring force is directly proportional to displacement. In oscillation also the restoring force is directly proportional to what? The displacement of the body. In spring also here the same. The restoring force, what the restoring force? When it just compressed like this now. When it just compressed like this, there the restoring force is there. Here the applied force, then it is moving upwards due to the what? The restoring force. Here the restoring force is there. Okay. In this spring, we have to discuss some important concept here. And what is the form of this spring constant or spring pendulum, spring constant? What is the restoring force here? What is the time period of the spring? And what is the frequency of the spring here? First one, if it is continuously elongated and another one is compressing like this. Compressing always. One thing, when it is just elongated and compressed is there, I will take this only this diagram. The restoring force is always directly proportional to the displacement of the body or displacement of the particle. When you remove this proportionality sign, it means what? The restoring force is directly proportional to displacement. The restoring force is always towards the mean position and the displacement is always away from the mean position. It means what? It is a mean position, this is the mean position of the body. When it is elongated like this now, when it is elongated like this, due to the mc is there, applied force is there, displacement is y. Y is there. But the restoring force is opposite to the applied force, it is opposite to applied force. The same displacement is there, but initially the displacement is obtained due to this one. Here, this displacement is always what? Away from the mean position. It is a mean position. It is always away from the mean position, but the restoring force is always what? Upwards. Upwards. That is, both are in opposite direction. So that FRE, it is minus of. It is directly proportional to minus of y. It is directly proportional to the displacement of the particle. When it is the proportionality sign is removed, then we have to apply one constant, that is k, that is equal to minus of y is there. I want to derive here what is the time period of the simple. What is the time period of the spring pendulum? Time period is nothing but what? It is continuously oscillating for time period for 1 revolution. Okay. If the restoring force, consider restoring force as ma or mg is there, right? G is nothing but what? Here, opposite to that equal to a. Here, taking m into a. Then it is equal to what? into y. K into y is there. Then mass is the mass of the particle, it is constant. A is nothing but what? Sorry, it is considered as a capital. A is nothing but what? A is an acceleration of a particle, where A is acceleration of the particle executing simple harmonic motion. Then A equal to what? Minus of omega square into y is the displacement of the particle. Okay, this is the form of acceleration of the body. Then if you substitute in this equation, m into minus of omega square into y is equals to k into y. Here y gets cancelled. Then minus also gets cancelled here. Then omega square is equal to what? K divided by m. If you remove or taking root both sides, then omega is equal to what? Root of k divided by m. Consider this k is the spring constant. What is that? It is called the spring constant, or it is also called the spring factor. And this is a mass. We already know in that Newton's laws of motion that mass is considered as an inertia. So that here it is a mass considered as an inertia factor. It is under root like this. If you want this omega is equals to spring constant, root of spring constant divided by inertia factor is that. If you want the time period, then what about time period? But the time period, if you want the time period, that is t, but the one form is there. Omega is equals to what? 2 pi divided by t is there. Then you can take t is equal to what happen? 2 pi divided by omega. Then t is equal to omega is in the denominator, that become what? 2 pi root of reciprocal of this one. What happened? Inertia factor is m and spring factor is k. This is the time period of it. Then what about the frequency? Frequency of the spring pendulum is nu is equal to 1 by t reciprocal of time period is there. Then directly, if you write its reciprocal form, that become nu is equal to 1 divided by 2 pi under root. These also become what? Reciprocal. Then again spring factor divided by inertia factor, that is mass of the particles. Using this one, can take that some problems on this spring pendulum. Okay. In next class, we'll discuss about some examples of that. Thank you.